Hello. Can you all hear me? My name is Alexander Baker. You guys can just call me Alex. And today I'm going to be going over a very interesting topic called survival modeling or survival analysis. It's a pretty interesting realm of statistical analysis that can be very applicable to a lot of areas, especially if you're at like a dead end and don't really know how to proceed forward with a particular problem. Like this can definitely, ooh, this can, hello. I see that we have a lot of new participants. I'll start over. My name is Alexander Baker. Today I'll be going over the topic of survival analysis. It can be very helpful for a lot of business problems, human resources, especially and experimental performing experiments. It's very useful for that as well. So so I feel like this is a very important topic in statistical analysis that's always kind of flown underneath the radar, and I would love to bring more attention to it. For those of you who don't know me, my name is Alexander Baker. I have worked at companies like KPMG and Booz Allen, supporting clients like the FDA, the Air Force, the DHS, and other departments within the DoD. This is something that I have incorporated a lot in the workplace, and I feel like it's a pretty cool realm of statistical analysis to share. So I'd love to get into it. Oh yeah, and by the way, like please ask me questions along the way. I'll do my best to answer as many of them as possible as we proceed with the presentation. Let me minimize this. So what is survival? So as you can see, I added like that little a little image of what is traditionally known as survival. But what do I mean by survival? The main purpose of survival is to essentially analyze and model the time an entity spends within a system before a particular event occurs. So you can kind of think of it as like think of having a population of cells, right? And at the start of your system you have 10 cells, and as time goes on you can consider an event in your system, apoptosis or cell death. And essentially what you're doing with survival analysis is you're measuring, this is literal survival analysis. You're measuring how many cells survive, or what is the rate of cell death at a specific time within your experiment. So your event would be cell death. The observation period will be like how much time you allot for to analyze the cell apoptosis. And essentially, at a particular the event would be that apoptosis that you're trying to measure. So that's essentially what I mean by how much time an entity spends within a system before a particular event occurs to said entity. And survival analysis can be particularly useful for analyzing the number of incidents that occur at a particular time, analyzing the number of affected individuals at a particular time, the probability that an individual will spend this much time in a system before a particular event occurs. And kind of the basis of this talk going forward is I'll consistently be swapping between two general survival techniques, and I'll jump into them more. There's survival curves and hazard functions. You can kind of think of the difference as a survival curve measures the probability that an individual survives given a specific amount of time, and a hazard curve essentially models the rate at which a number of events occur within the system at a particular time. So with that said, let me kind of talk about like the basics of survival. So I gave this the general example of cell apoptosis, but this is kind of going to define like each specific term of what I meant within that example. So first thing you want to do is you want to define the system that you're looking at as a whole. Like, like essentially what do you want to analyze the entities within, and like what, and essentially, for example, like your system can be a workplace, it can be a cell culture, it can be essentially like a number of machines at a factory that you want to analyze the failures with, or the time until failure. So defining your system is a pretty big. It's pretty important to start establishing all of the other factors that we have within our survival analysis. Next, you want to define your observation period. Like typically, your observation period can also be derived from the data, but you want an idea of how long you want your survival experiment to go on for, your survival analysis to go on for. Like, typically in the workplace, you probably don't want to, you probably don't want to analyze, or it might be a little bit much to analyze, especially if your company's over 100 years old. If you're analyzing turnover rate, it might be a little bit difficult to analyze turnover rate like 50 years ago because there might not be data available at that point. So it might be smart to kind of narrow down your observation period. And on top of that, you might not want to observe till the most recent date. You might want to observe the company's turnover rate from one time to another, from one specific time to another. So observation period is another like very important factor in creating your survival analysis. And then you want to define what your event is, like what in particular occurs to an entity within your system that will make it leave the system, essentially. And it can be like a cell death, a termination, quitting, or any type of employee attrition uh, that can cause them to leave the company, or like a machine failure. It's important to define this because this is pretty much the basis of what you're going to create your survival model with, and then what the entry point is. So this is another very important thing. The entry point is essentially when you create different timelines. So I'll go into how survival models are created because within survival, you don't actually have the actual dates when you do it. Typically, the time within the system is measured in discrete time units, depending on what kind of units you choose. So defining the entry point is another one of the most important factors in a survival analysis because the entry point to the exit point is essentially how you find the amount of time within the system. And I'll get into that more in depth later in the slide. Um, Next is you want to make sure you select the appropriate discrete time units. So if you're looking at company turnover rate, it might not be very helpful to look at it on like a minute by minute basis, right? You might want to. It might be more useful to look at turnover rate on a month by month basis, on a year by year basis, when you're defining when you're looking at how much time an individual spends within this system before, or within this company before they separate for any particular reason, you know. So saying like, oh, the average individual spends 10 years at this company before they separate may provide more it may provide more information, or it may be more useful to your stakeholders rather than saying, oh, this individual spends 1100 minutes in in here before they separated. So it's important to kind of consider that before it's important to kind of consider that before you I'm sorry, when you're making your survival analysis. Um, Next, you want to next. I kind of touched on this before, but you want to define your timeline, and essentially, your timeline is the point of entry in which an individual enters the system to an event occurrence or the end of the defined period. Now, this also touches on why you want to define your observation period very well, because because if an because individuals in survival analysis don't have, like, all individuals in survival analysis don't have to have the event occur to them by the end of the observation period. And that's kind of the strength of survival. And I'll get more into this later, but the strength of survival is taking that into account, that unknown of when the event actually occurs to certain entities within your system. So anyway, the timeline is kind of defined as your point of entry to either the end of your defined period or that event occurrence. And this is another factor in which survival models are based on. And you can kind of see it here. You can see here, the X's are when the events occur. You can see like various timelines. This person spent about 8 months in the system. This person's entry point was at, it looks like 3 months here. They lasted to the end when an event occurred to them. This person, you can kind of see, like when people fall out, when certain people had events occur to them. So just just pretty interesting to look at with this illustration. Next is typically the start of your period is usually defined within the data. You can either have a defined starting point for your observation period, like all the cells enter the system at this time. You can manipulate it so all factors enter the system at a particular time, or you can define it as like when they were hired, when the part was created, so on and so forth. Now, there will be instances where you don't know the specific, there will be instances where you don't know the specific starting date of particular entities, and there are ways to handle that. I'll go into it a little bit more, but there will be instances where it's kind of where your starting date is cut off. But most of the time, you'll have that entry date for. It's important to have an accurate, reliable entry date for a lot of your entities within the system. Then the end of your observation period. Typically, most of the time you'll see it as the latest date within your system, but sometimes the latest date within your data. But sometimes you'll want to. Sometimes you'll want to choose a specific end date for when you want your observation period to terminate, and it's important to have like a specific reason behind that. Then you have the event occurrence, essentially what removes the entity from your system. It can be a machine failure, a cell death, a cell death, an employee leaving your company, or employee attrition. So that's also like variant. So that's also another base of survival. And then this is something interesting, and this is a very important term. If an entity reaches the end of your period before an event occurs, that entity is known as it's known as censored data. So, and it's called that because it's unknown when that specific entity, the event will happen to that specific entity. And the strength of survival is that it allows us to create models around this censored data in order to. It allows us to create models around this censored data in order to create accurate and efficient analysis. And this is something that can't be done with like traditional machine learning methods that you've seen, like random forests. There are survival counterparts to a lot of the traditional machine learning methods, but this data censorship is why a lot of traditional machine learning methods have difficulty with survival analysis. So I'll stop there to see if I have any questions. How do I pull this up? So there's a QA. How do I pull up the questions? Is there more? I can just keep going and answer questions at the end of the PowerPoint, and then we can move on to the code. So Next, I want to get into what is known as a survival curve. So with this specific example, we're going to explore the Kaplan-Meier method. Now, Kaplan-Meier is essentially just a very basic, it's a very basic concept of survival curves, and this is essentially to analyze what proportion of our population is surviving at a particular moment in time, and it essentially drops off as time units within our system increase. You can see drop offs at a particular amount of time. So essentially, this answers the question: what is the probability of survival? What is the probability of survival at time? Well, like, what is the probability that a cell will survive 10 minutes into the experiment? That particular question. So I will get into more of the equation. Essentially, each fall is the number of unaffected individuals over the total number at risk. And this is multiplied by the previous fall. So essentially, each fall is multiplied by all of the other ratios together at each particular fall within the curve. So another thing to point out is how Kaplan-Meier curves handle censorship. So when an entity is censored within a Kaplan-Meier curve, the number of at-risk individuals, which is essentially, you can think of it as the number of individuals within our system that haven't had an event happen to them yet. The number of at-risk individuals will decrease by 1, because, as you know, since an individual is censored, they're leaving our system, but they're leaving our system. So an event cannot happen to them, since an event cannot happen to them. So they will not be affecting the rest of our survival, the rest of the survival curves, like, moving forward. So here's an example I created of a Kaplan-Meier curve that I did myself, and I kind of walked through the calculations here just so we can go over it a little bit. So basically, our Kaplan-Meier curve will start at time equals 0, and 10 cells will be in our experiment, and this will be 100% of the population. At time t equals 2, 2 of our cells die off. So you can see a drop in proportion by 0.8, since our remaining our unaffected individuals at this point were 8, and there were 10 at risk. So 8 out of 10, 0.8, and you can see our curve drop down to 0.8. This is when it gets tricky. So this is where I add a little bit of a curveball. One cell is censored, and what that means is at t equals 3, say our experiment is 10 minutes long, right? This experimenter, for whatever reason, decided to add in a cell at minute number 7 within our experiment. And that cell lasted 3 minutes because they were added at minute number 7. They lasted till minute number 10 at the end of the experiment. And then their timeline is essentially 3 minutes within the system, but an event has not occurred to them yet. So they are leaving the system without an apoptosis occurring. Like, our experiment ended, and the apoptosis didn't occur, or the cell death didn't occur. So that cell leaves the system, and you can see that there's no drop at 3 here, because that cell left our system without the event occurring to it. So going to the next one, you see at t equals 5, another 2 cells drop off, and the proportion and our new proportion will be calculated 7 minus 2 divided by 7. And you can see that that censored cell effect, that's the censored cell effect right here, because if that cell wasn't censored at t equals 3, it would be 8 minus 2 over 8. But instead, it's 7 minus 2 over 7, because that cell has left the system. So technically, even though only 2 cells have died, we have one cell that has we have one cell that's not being included in our system. So so the total number of missing cells at time t equals 5 will be 3. Now it'll be 7 minus 2 over 7, which will be 0.714. And then this will be multiplied by our previous drop, 0.8, for about 0.57, and that's where our new survival probability will be. And you can see it reflected in our survival curve, because you can kind of see the drop falls a little bit under 0.6. Next, I threw another curveball at time t equals 7. At time t equals 7, 2 cells are censored. So similarly, let me go over this again, because the censorship is very important, and I feel like I haven't been explaining it well. But let me go over this again. So at t equals 7, this essentially means that these 2 cells have lasted 7 minutes within our system before they were censored. So essentially, these cells were added at time t equals 3. So at minute 3 within our experiment, and they lasted 7 minutes to minute 10, and apoptosis has not occurred to these cells. So these 2 cells lasted till minute 10 and left the experiment without apoptosis occurring to them. So at 7, you don't see a drop, but 2 cells have left our system at this point. And that leads us to essentially at t equals 10, I said 3 cells drop off, and you see 3 minus 3 over 3, which is 0. 0 times 0.714 times 0.8 equals 0. So you can see that our curve drops all the way down to 0 at t equals 10, because the remaining 3 cells die off at t equals 10. So this is just a toy example that I made up, to kind of, like, a very simple toy example I made up to kind of explain the concepts I've been going over in the context of a Kaplan-Meier curve. Moving on, I want to go over a hazard curve, because this is another very important concept within the whole realm of statistical survival. So this method is called the Nelson-Allen survival curve, and essentially what it does is it's the sum of the ratios of the number of events over the number of at-risk individuals. So essentially, you're calculating it's essentially the cumulative rate at which events occur within our particular system at a particular time. And it's very similar to the Kaplan-Meier curve. The main difference is that this is a cumulative curve. So we're measuring the rate at which events occur in jumps, and we're not measuring the proportion of unaffected individuals or the probability of survival. We're essentially measuring the rate at which these events will occur within our system at a particular time. So that's why these are typically used. That's kind of the intuition behind them. Now, similarly, if an entity is censored, it leaves the system, but there's no jump that occurs. And you can kind of think of it as this in the same way, where say we add in cells at minute number 8 out of our 10-minute experiment. They last until minute number 10 and no apoptosis occurs. That would be that cell will have a timeline of 2 within our system, and it will be censored at time t equals 2. So just an intuitive way to think about that. Likewise, I added a hazard curve right here as a sample for you all to kind of wrap your heads around. In order to get behind the intuition of it, so our hazard rate will start at 0, and at time t equals 2, similarly, 2 cells will die off. This means that our hazard rate will increase by 0.2, because 2 out of 10, 0.2, number of events over total number of at risk. And then at time t equals 3, one cell is censored. So that cell was added at minute number 7 within our within our survival analysis, and it lasted till minute number 10. And upon reaching minute number 10 within the survival analysis, that cell apoptosis did not occur to that particular cell. So that cell leaves our system, but it still is measured at time t equals 3. At time t equals 5, 2 cells die off, and our hazard ratio will be 2/7. Remember, 2 cells die off from the previous one, plus 1 cell that is censored off, and our new hazard ratio is 0.28. So we add that to the previous system, we get 0.58. You can see a jump right underneath 0.5, or not 0.58, 0.48, because that's 0.2 plus 0.28. So you can see this the jump in our hazard curve to just under 0.5, and that's you can see that that's our hazard rate by that particular moment. It's the sum of the previous 2 jumps. At time t equals 7, 2 cells die off. This is equivalent to us adding in 2 cells at time t equals 3, and they last until t equals 10, but apoptosis doesn't occur. So those 2 cells are taken out of the system. At time t equals 10, 3 cells die off, which will be 3/3, so it'll be 1. And then that 1 will be added to 0.2 plus 0.28, which equals 1.48. So that's the hazard ratio. And you can see the jump to just under 1.5 for that hazard curve. Let me see if you will have any questions. Sorry about this. I have so much trouble with it. I think this is no open questions. Okay. Let me get back to the slideshow. So the next thing I want to go over is censoring. So I kind of touched on this briefly before, but I can record, but I can go over it again just to make sure that because this is essentially the cornerstone of why I'm going over all this stuff. Like, this is the cornerstone of why survival analysis is so important in the first place. So in survival analysis, not in a system, an event can happen to all of your entities. However, it will not have. However, oftentimes the event will not occur to all entities within your system within your observation period. For example, if you're looking at turnover analysis at a particular company, not all employees, it would be a pretty bad situation if all employees quit by the end of your observation period. So most of the time you'll have a number of employees that stay by the end of that observation period. And those employees, since they haven't left the company for any particular reason as of yet, those employees will be known as censored employees, specifically right-censored employees. Now, because essentially that uncertainty is what is taken into account when survival analysis is accomplished. So essentially, you can kind of think of censorship as uncertainty at which a certain event occurs. And I'll be going over the different types of censorship. Typically in survival analysis, you'll mostly encounter right censored data, but I want to go over the other types of censored data just in case certain censorship occurs at that particular time. Just in case just in case your data contains this. So going over again, I really want to emphasize this point. Censoring occurs when an event is unknown, because this is essentially like the pinnacle, the reason why survival analysis was created in the first place. Left censoring data is when the event occurs to an entity before your selection observation period starts. So say, for example, you're running 2 cell apoptosis experiments, right? And in your previous experiment, you started it at day April 13th, right? Or you started it at time t equals 0 to t equals 10. And then you start another apoptosis experiment from time t equals 15 to t equals 25. essentially, if your observation period, you're only looking at the observation period of t equals 15 to t equals 25, the cells that die from t equals 0 to t equals 10 will die before your observation period actually begins within for your experiment. So what ends up happening is that those cells are considered left censored data with if your observation period is from t equals 15 to t equals 25, because those cells experienced the event or apoptosis before your experiment had even begun. So that can be an example of left censoring. Right censoring, say you add a cell at, again, like I'll go over it again because it's very important. Say you have say you have an experiment from t equals 0, like minute 0 to minute 10, and you add in a cell at minute 5, and that cell that you added in at minute 5 goes to minute 10 without experiencing apoptosis. That cell is considered right censored because the cell did not experience the event within your given observation period. Next, this is a little bit more complicated. So interval censoring data is when you know that an event occurred within a specific amount of time, within a specific interval of time, but it's unknown the exact time at which the event occurred. So it's kind of like saying, oh, it's kind of like having a very inaccurate monitor, or like a very inaccurate way to collect your data. And you know that, or say for some reason you want your apoptosis experiment to be to the nanosecond, right? If you're measuring the time a cell spends within the system, but your computer can only go up to, say, seconds, you're going to have to settle for, oh, the interval at which this event occurred is between 9 and 10 seconds, but the exact time, but since it's measured in nanoseconds, the exact time in which your cell had experienced apoptosis will not be known. So that is called the interval censored data, because it's known to occur within that time frame, but the exact time is unknown. So very complicated in dealing with it. I'll talk about a really cool method with it. I won't go into detail about the method in dealing with interval censored data, but I highly recommend looking into it because it's so clever. So handling censored data is pretty important is in survival analysis. So I kind of want to start out with left censored because it can be pretty simple to handle or complicated depending on your situation. But essentially, if your data is left censored, you can handle it by dropping it or extending your period of analysis to include the left censored events and the left censored entries. So like, say we have, again, like going back to the previous example, we have an experiment of cells at, we have an experiment measuring cell apoptosis from time minute 0 to minute 10, and we have another experiment measuring apoptosis from time minute 15 to minute 25. If our observation period is minute 15 to minute 25, we can extend our observation period back to minute number 0 to include the apoptosis from minute 0 to minute 10. Now, there will be a little bit of bias that will be introduced in this example because there won't be any apoptosis from minute 10 to minute 15, but it's just the same, like a suggestion of what you can possibly consider. Or you can just ignore the experiment from the observation window from minute 0 to minute 10, but sometimes you have very limited data and you don't want to ignore them, so it may not be an option. But just some examples. Right censored data, essentially there's an output variable as well as a time variable that's incorporated as part of your output that the models are fit on. Survival models are geared towards handling right censored data, and that's kind of the purpose of them. So right censored data is handled within survival analysis by having the outcome considered, as well as by deriving a probability or some type of hazard rate by both considering the event occurrence and the excuse me, the event occurrence and the time at which it occurs. Interval sensor gets tricky. So there's something called the Turnbell approximator, which is an iterative method of continually fitting a survival curve to a particular continually fitting a survival curve to the interval of which a particular event had occurred. And essentially, it's a method of estimating the number of events that had to happen by using the interval, in which is established by your data. So really, really cool. I read a lot of. I went down a big rabbit hole for Turnbell approximators. Read some really cool papers about it. I recommend looking into it if you're interested. It's a very, very neat method and a cool subset of survival analysis. One Another method you can do is just create create kind of almost confidence intervals where you have the upper bound, the lower bound, and then the midpoint, and you can create your survival analysis out of that when you have interval sensor data. Just some suggestions for handling this because it can be very complicated. I want to emphasize there is no right answer. This topic is hotly debated by statisticians in the most prestigious universities. So these are just some suggestions I found by reading academic papers and surfing the web. So I thought I might just relay them to you guys. So now you might be wondering, hey, if we look at these survival models going up here, these don't have a lot of predictive power. Like, yeah, we can interpolate the data by saying, oh, if our example in our cell apoptosis example, say we want to predict the probability that a cell will survive 7 minutes within our system, we can do that. But if we want to predict that a cell will survive more than 10 minutes, that won't work because it'll just be 0. So what's really cool is very smart people looked at these survival curves and realized, hey, these survival curves create a set of points that a function can be fit to, that a parametric function can be fit to, that we use for other risk distributions. Why not fit these risk distributions to our particular functions in order to create our own survival curves that we can extrapolate with? So people invented parametric methods to be used with these survival curves. And these parametric methods can be fit using numerous methods, mean absolute error, MSE, goodness of fit. Essentially, you find the best parameters. You use parametric functions like Weibull functions, Weibull functions, log normal functions, Gauss exponential functions, and you create a survival curve by fitting by finding the optimal parameters for these functions. Now, the reason why you would do this is to solve that problem before the extrapolation, because by fitting these functions to your survival data and your hazard curves, you're able to further extrapolate. Say you're able to find out if your experiment is from time 0 to minute 0 to minute 10, and you want to see how many cells survive to minute 15, you're able to find that out. And remember when I said it might be a little bit of bias because we don't have any data from 0 to 15, like we'll be able to find that data by fitting a model to it a little bit better. So really cool concept. These parametric models, something very much to keep in mind when you're doing your survival analysis. Now, one thing that I want to get to before moving on to some really, really cool stuff is if you want to compare survival curves, there's a statistical test called the log rank test, and this is something that I kind of want to put in the back of your minds to essentially if you're doing survival, like you'll say, oh, like if I want to compare the rate of survival between two individual groups, the log rank test is a fantastic way to do it. And essentially, you can kind of think of it as a modified chi-square test where it compares the values for two various survival curves. And essentially, the null hypothesis is that there are no differences or that they're derived from the same population. And then the alternate hypothesis is that there is a difference between the rate of survival between these two groups. So one thing that I want to end this with is it's an important building block for a lot of statistical for a lot of survival models, especially when you start getting into random survival forests and decision survival trees. Log rank test is very important. So something I just want to plant in your mind. It seems a little bit disjointed, but when you start researching more sophisticated survival methods, it tends to be very important. Going to the Cox proportional hazard model. So this is when we get into some really cool stuff with a lot of this. So the Cox proportional hazard model can kind of be thought of as a way to implement covariates within your survival model. So essentially what it does is you can see this equation up here. You you essentially perform a certain type of linear regression, or almost a certain type of regression, by fitting by finding the impact that certain covariates have on your baseline survival curve. And this in turn ends up influencing particular, or technically it's a hazard curve. So this in turn ends up influencing particular hazard curves, and survival curves that it's fit with hazard curves, but you can modify this to be a survival function as well. But essentially what this does is it influences the baseline hazard curve and creates unique hazard curves for each entity within our system based on their intrinsic attributes that can be found by multiplying them via this covariate function. So it's a really cool method that allows different attributes to have an effect on our hazard curve within our system. So if you're performing an analysis on employees, whether they want to stay at a company or not all employees have the same attributes. Some employees have different vacation benefits, or some employees have different time off plans. Some employees are at different levels within the company. There are lots of different attributes within employees that could affect their survival rate, or not their survival rate, technically. There's a lot of factors that could influence whether an employee leaves or not. And this is where Cox proportional hazard comes in very handy, because you're able to take those into account. I'll go into more details about it, and another interesting tidbit that I wanted to add is essentially you can get what is known as the hazard ratio by taking the exponent of the coefficients within the Cox proportional hazard by singular coefficient. And that's why it's called the proportional hazard, because you're able to essentially isolate like different hazard ratios using this Cox model to gain more analysis on how much of an effect a particular feature or covariate has on a particular event occurring within your system. So very important to keep in mind. So something I wanted to kind of get in here that I found really interesting was how the Cox pH model, or proportional hazard model, is fit. So it's important that it's fit even though it's very similar to regression, it's fit differently from a regression in that it tends to minimize the negative log partial likelihood, or the negative log likelihood of or technically it's like negative log partial likelihood of a particular event occurring. So basically it takes into, remember when I said the purpose of survival is to take into account that data censoring? That's where this fitting comes in, very much comes in handy, because the fitting of the Cox proportional hazard model essentially wants to maximize the chance of saying an event occurs at a given time, given that it does. So this is its way of taking into account event censorship and or data censorship while fitting this data. So this maximizing problem is then changed to a minimizing problem by changing it to a cost function, the negative log likelihood. And essentially, this the reason why it does this is that it has a universal minimum that can be fit to, and this way we can find the optimal parameters for our Cox pH model. So really cool stuff here. I certainly recommend reading papers on it because a lot of people explain this in a lot more depth. I just want to give you like a bird's eye view of how these are fit, just so you kind of have a general idea of the intuition behind it. But I recommend looking more into the actual like math behind this because it's really, really cool. Um, so basically, when you create your Cox pH model, you're given a summary, and this summary includes your coefficients. So so essentially how certain covariates influence your baseline hazard curve, the hazard ratios, which is essentially the comparing the instantaneous hazard rate of various of an affected covariate hazard curve versus the baseline hazard curve to see if that covariate makes a difference. Below one indicates a decrease in risk, above one indicates an increase in risk, and about one indicates a lack of association. So it's important to keep that in mind when analyzing the hazard ratios. Now, another thing that you'll see included is that I believe in the summary, I looked it up all over. I believe it's the log rank test in the summary, but essentially there's a statistical test of the difference in survival curves between the difference in hazard curves between the baseline and the baseline and the affected covariate one. So really cool to keep in mind. Now, if you remember, I went through the regular AFT, the regular Kaplan-Meier and the Nelson-Allen fitters. I want to go, and then I went through the parametric versions of that. Well, I want to go into the accelerated failure time model the accelerated failure times or AFT fitters. Now this is essentially the parametric counterpart to our Cox pH model. So this is essentially how we can forecast survival probabilities and hazard rates based on individual unique covariates. So this combines what we went through the Cox pH model and the intuition behind the Cox pH model and the parametric models to create essentially a parametric survival model that's able to be fit on numerous covariates. So you can kind of think that these equations, they do differ depending on the parametric model that you choose. In this example, I did the Weibull. Excuse me. And essentially they're called accelerated failure times because they are the failure rates are either increased or decreased, or the failure times are either increased or decreased depending on the covariates within those models. So really cool. I'll go into, I have some demonstrations later. So kind of what I want you to, so this is kind of the general summary of the whole thing. It's very important to keep in mind like what survival is. It's the time an entity spends within a system before an event occurs. You have hazard functions, which are based on the proportion of incidents over the number of at risk. The survival curve, which is based on the number of unaffected entities over the total number of at risk at a particular time. And then you have your parametric curves, which allow you to forecast or extrapolate these hazard rates and survival probabilities. And then you have your Cox pH and AFT fitters, which essentially allow you to add covariates into the equation and create unique survival models based on that. Now, going into next steps, I have tons of really cool methods to look into. So we have our survival trees, which you can kind of think of survival trees as the survival counterpart of decision trees, where essentially each method is split on essentially the splitting is determined by log rank statistics, and then the tree is created based on that. And then the survival forest is essentially like a collection of survival trees. So, and then you have the survival vector machines as well, which is of course like the counterpart to support vector machines. And then people have been working a lot with survival analysis and deep learning. So really, really cool stuff here. I believe this is. I'll only be going over lifelines within the library lifelines within this demonstration, but it should be noted that if you want to go into the more advanced, the more sophisticated survival methods, there's a library called PySurvival, which will have these methods available to you. All right, and I believe so. I want to get into the. I kind of want to get into the code really quick. I have about 10 minutes to get into it. So in here, I use the library lifelines to essentially create our baseline survival models. I downloaded. I have an example with. I have an example with what I call a toy example, which is just one of the data sets within lifelines, and one of the data sets within lifelines, and then I have like a real data set that I found on Kaggle. So we first start off with getting the head of our data just to see it. Really weird stuff going on with sex over here, where it's a binary between 1 and 2. So I use the label encoder to change that. We extract our time and our event. The C is the event in this one, in this particular data set. So we extract our time and our event column, and we use our the Kaplan-Meier curve to fit it. Make sure to define the observed event within our Kaplan-Meier curve. And then we use our Nelson-Allen curve to fit our hazard curve. So now we have our Kaplan-Meier curve, which you can see some interesting stuff right here. You can see some interesting stuff right here as it decreases over time. And then we have our Nelson-Allen curve, which you can see the rate, the cumulative hazard rate, like increase over time. 40 years, interestingly, you can see like a general drop off then. Next, this is an example of the log rank test where we have our male group and our female group, and then we use the log rank test to get results. You see that these do not seem to be significant in this particular example. Next is the example of the parametric fitting for the Weibull curve. You can see like the general decrease. So this is the Weibull fitted model for our this is the Weibull fitted model for our data. And then we're able to incorporate other features using the Cox pH model. So we define our DF here, what our time column is going to be called, and then our event column. And then, as I said before, we print the summary here. You can see our coefficients displayed, the EXP of the coefficients, which remember is the same thing as the hazard ratio down here. And you can see some standard error, and you can even see the results of the statistical test. So you can see that age tends to have quite a bit of a age tends to be quite different, has a different effect, and you can see that sex is not significant. So interesting stuff here. Then you can start creating your unique survival curves based on your unique survival curves based on individual covariates. So really cool stuff here. You can see that there's a lot of some covariates have like certain effects and can completely change the shape of the survival curve. And then with the hazard curves too, you can see that different hazard rates are affected depending on the presence of various covariates. And then we can take so in this example, I'm doing the Weibull AFT fitter, but there are other AFT fitters that you can try. But in this example, I wanted to parametrize the Cox pH model, which is technically semi-parametric, turning into a full parametric model. You can see how it's kind of smoothed out. It's turned into a function that you can forecast with. And then you can see the hazard curve is also forecasted. And then by inputting the time that you want it and the features, you can predict it. So the end of this is at 40. I predicted at 50 right here. So some really cool stuff. It predicts the survival model at 50 at T plus 50. So pretty cool stuff here. Um, I used the turnover set to kind of add in some more spice with this. Essentially, you read in the data set. It's interesting. I'm going to upload this to to GitHub repository and have you guys play around with it. But there are tons of variables that you can play around with in this data set. That's why I like it so much. For this, remember, our system is, since this is turnover rate, we care about the years of the company. We don't really care about years of the current role or years with the current manager. It's important. One of the assumptions for Cox proportional hazard is to make sure that your features are consistent with time or independent of time. So like if years with the current manager might affect that. So I just picked it a select number of like safe variables, but you can pick a lot more. So interesting turnover rate. You can see like more people tend to stay at a shorter time than a longer time, which is expected. Surprisingly, especially considering that like there's a lot of censorship within this data, like a lot of people didn't leave. And then you can see like the years of the company and the attrition rate are time and events. You can see that you can get a good look at our Kaplan-Meier curve, repeating the same process. But you can get a good look at our Nelson-Allen curve. You notice that our confidence intervals tend to be a little bit slimmer since we have more data in this. Then we change this into parametric models. Some pretty interesting stuff going on there. We can use this to predict the turnover rate beyond this observation period. Then I chose a select number of variables here to take a look at. I did a little bit of EDA here. Some interesting stuff. You can see some, this is interesting, the age versus years of the company, which of course you expect. Maybe age isn't the best thing to do in this situation, but again, like you can pick your own. Some interesting EDA. Again, like the purpose of me doing this is so that you guys can perform your own. And then I use the Cox pH fitter on this data. You can see some interesting stuff right here. Like age doesn't have much of an effect on this. You can see that monthly income is also pretty inconsequential. You can see that gender does have an effect on the attrition rate a little bit. Not so much. And then you can see like environmental satisfaction and age, like it's saying that they do. And again, like really cool stuff that you can play around with here. The hazard ratios tend to be like all around 1, but you can still see that it's statistically like some of them are very much significant when their hazard ratios are close to 1. So it's important to keep it in mind, like you want to look at everything when doing this. Then you can take a look at unique survival curves right here by taking your inputs and inputting them into the predict survival function. Then you can also take a look at your unique cumulative hazard curves by taking your covariates and then putting them into the cumulative hazard functions. And then finally, like you have our AFT models for this example. You see the intercepts are added here, and you can also take a look at some additional analysis with your AFT model. Now we have a model that we can use to predict unique parametric functions and unique hazard functions and also extrapolate with them. So that's pretty much like the basis of survival model. Like this is just scratching the surface. I highly recommend looking into more of the advanced topics and more of the advanced topics and more of the model methods that require a lot of deep dives, because survival can be really, really cool. And it results in using these models can result in like creating cool dashboards where you can essentially look at the age, look at see how much time somebody spends, predict the probability of survival at a particular time. So at time t equals 40, we have 0.629. you can forecast it outward. So 0.566. So you can create really cool products where you can essentially analyze the rate at which the attributes that affect like particular survival rates within a particular company. You can change the age, and then you can predict, given these attributes, what is the probability of their survival. So really cool stuff. I'll post this code. I purposely made the Streamlit code for this dashboard very like just a very simple script, so it'll be easy to follow along, even if you're not a pro at Python. So yeah, that's pretty much it for me. I appreciate you all for listening, and I really hope that you learned a lot about survival. Again, I wish I knew how the I wish I knew how the questions work, because I do not see any Q&A stuff around here. Yeah. Yeah. I'm very happy that you enjoyed it. Yeah, I'm very happy that you all enjoyed it. Thank you for sticking to the end. I know it's a lot of very dense information. It can be a lot to it can be a lot to digest all at once. So I'm very happy. I love that comment. You can say we survived. I'm very happy. I'm very happy you all got a lot out of this. I could do a survival analysis based on the people that started. The observation period can be like the time the talk began and the time the talk ended and the number of people who dropped off. Man, that could be a survival. That could be a survival analysis in and of itself. Yeah. Thank you so much for tuning in. I'll definitely share this. I'll definitely share this code in the future.